Welcome and thank you for tuning in to this video with me, Dr. Loay Al-Zube. I am continuing a series of videos about biomechanics, and in this specific series of videos, I'll be talking about the linear kinetics of human movement. I would like to highlight that I will be talking in this video about the factors that affect friction and what is friction, and also what is the role of friction in daily activities and sports. And that's what is important for us from a biomechanics point of view. So I will start by defining friction. So what is friction? So friction is a force, and it is acting over the area of contact between two surfaces, and the direction of this force, which is the friction, is opposite to that of motion or motion tendency. And the friction force is quantified in newtons. That's the unit of this force. We have a formula to calculate the magnitude of this force, which is the product of the coefficient of friction, mu, and the normal reaction force. So we can write F equals mu multiplied by R, and F is our friction force. And if you recall from statics and dynamics, we talked a lot about this, and we solved multiple questions and problems. I will go over the concept briefly, and then we will be able to use it in problems and questions related to biomechanics. So let me first of all show you a schematic of a free body diagram of an object sitting on a table. And if you recall from our previous knowledge of statics, we have the weight of the object, and that weight is directed downward. So this is the direction of the weight going down. And we have also a reaction force, which is the table pushing on the object up. We don't have any horizontal applied force because the object is not moving on the table. This square object is not moving on the table. We don't have friction and we don't have motion. And if you recall from our understanding of statics, we said to have this object in equilibrium, summation of forces in the x-axis should equal to 0, and summation of forces on the y-axis should equal to 0. And that's why we have a two-dimensional object now here, or a schematic, and that's how we have equilibrium, and the moment equal to 0 as well. Because of that, so the laws of reaction, the forces acting with the box, are only the weight of the box, which is the mass multiplied by the gravitational force G, which is mg, right? And we have also the reaction force R applied by the table, and that is equal and opposite in magnitude for the weight. That's what we have in this free body diagram, or a schematic that represents the free body diagram of the box sitting on the table. If this object is now experiencing a force, a horizontal force, then we need to introduce the friction and the concept of motion. So we are going to introduce two things, something called the maximum static friction and also the kinetic friction. And we're going to start explaining those because those are very important concepts. So the maximum static friction, that's also an important. We have static friction, we have maximum static friction, and we have kinetic friction. We would like to explain. So the maximum static friction is actually the maximum amount of friction that can be generated between two static surfaces which are about to move. That's that's what we call the maximum static friction. So the objects. So if we use the previous example, we have the box sitting on the table, and what is happening is that you have the object actually sitting on the table, and if we are pushing the object horizontally before the object starts moving, immediately before it moves, that's our maximum static friction. And the kinetic friction is once the object is moving on the table, then we have a constant magnitude of friction generated between the two surfaces in contact during motion, and it's usually that is smaller than the maximum static friction. And that's something that you experience if you're trying to move something on a table, at the beginning it's hard, but when it starts moving, it will be easier to move that object. And that is because of the kinetic friction being lower than the maximum static friction force. And I'm going to show you a couple of schematics as well. So here in this schematic, uh, on the top left, this is our example that we started with. We have the weight of the box on the table, and we have the reaction force. The weight force and the reaction force are equal in opposite direction, and we don't have any horizontal applied forces, so we have no friction and no motion. Now, let's say if we have a force, an FA, now we are pushing the box from the left to the right, and we say that we have a small applied force. Because the force is small, it's not going to move the object, so we have a small friction force. And because the system is still not moving, the box is not moving, we have equilibrium, which means that the FA, the applied force, is equal to the friction force, because the summation of forces on the x-axis should equal to 0, and also summation of forces on the y should equal to 0. So the weight should always equal the reaction force, and we don't have a motion. Now, if we have a large applied force, and the object is about to move, it didn't move yet, but it's about to move. It's in that moment that it's going to be moving, any moment, any time. And now we have something called maximum static friction, where Fa equals Fm, the friction force, and that force is the maximum static friction, and the weight in the axis should equal the reaction force. Once the force is larger than what we have here, and the object start moving, or the box start moving, then we have the Fa larger than Fk. Now Fk is, now we change the name from m for the maximum static. So you have no motion, that's friction force, Fs static force. If it's Fm, it's the maximum static force, and Fk is the kinetic. So that we have the object is now moving, and Fa is larger than Fk, and motion is occurring. Um, and the forces on the x-axis, they are not equal, and the forces on the y-axis still are equal. Sorry, actually we're going to have to do some calculations, but there are no movement on the y-axis there. And this is how bodies will behave actually when we have friction. Now I would like to show you a schematic that represent the progression or the development of the friction force when we have the applied force and the friction force, how they develop. And this is it. So this is the schematic. And if you look here, we have the y-axis is the friction force, and the x-axis is the applied external force. So as we increase the applied force, the friction force is going to increase, but here the object is not moving. And we continue increasing the applied force, the friction force is increasing until we reach the maximum static force here. And this is the dashed line is the indication, is the amount of force needed to start moving the object. So from this point and to the right and onward, the object is moving, and you can see that after the large maximum static force, there is a drop in the friction force, that's kinetic friction force, and becomes constant. So the static force is developing and increasing linearly, and the kinetic friction force is a constant force. So for a static body, the magnitude of the friction force is equal to that of the applied force, and that's what we're seeing here, right, in this part. Dynamic bodies, the magnitude of the friction force remain at a constant level. This is the one below that of the maximum static friction. That's when exactly the body is start moving. This is a good time now to see if check our knowledge with a quick attention quiz. So I want you to read the question and then pause a little bit and see if you can answer the question. We have a 10-pound block is in equilibrium, and actually the key word here is equilibrium. So the object is in equilibrium, or the block is at equilibrium. What is the magnitude of the friction force between this block and the surface? So we have a block is experiencing a 2-pound force to the right. We have the static friction coefficient, and can you think of what is the magnitude of the friction force between the block and the surface. And you can pause the video for a bit and then see if you can have the correct answer. Now, if you coming back now and we are looking at this question, because it's at equilibrium, we need to make sure that the summation of forces on the x-axis should equal to 0, which means the friction force should also be in the other direction. That's a friction, and that should equal to 2 pounds. So the answer for this question is actually C. Another question about the directions. So we have a ladder AB and is positioned as shown. What is the direction of the friction force on the ladder at point B? So let's say this ladder is steady in this place, it's at equilibrium, and we know that the weight of the ladder goes down, right? That's the weight, and the friction should be opposing that weight, so we should be expecting that the friction should go up this direction. And actually that is the solution, and that is D. This is a quick couple of questions just to make sure that we are on the same page in understanding the concepts. Now I would like also to show you another question, but it's not a quiz, but it is something to think about. Is it easier to push or pull a disk across the room? And from your experience, you would be thinking, well, oh, it's easier to pull it, not to push it. And I'm going to explain to you why is why that is the case. So if you look at this schematic of the table, and we're trying to push the table, so here on the top part we are pushing the table to the right, and the bottom part we are pulling the table to the right. So that's the force P. That's where should be in this location. So P, yes. So if we are pushing, if you look at the if you want to resolve this force into two components, x and y, we will have one component going down this way, and the other component will be going to the right, and that's how we resolve this force into two components. Now, if you would like to look at remember that the friction force Fr, right? The friction force is mu, the coefficient of friction, multiplied by the reaction force. So the coefficient of friction is constant if you are pulling or pushing, but the variable is actually the reaction force. So you want to make sure if you are trying to optimize your performance, you want to make sure that R is as small as possible. But here, if we look at this, the pushing scenario, you have the R should, we don't have movement on the y-axis, which means the weight plus PV, that component that was resolved because of the force or the pushing force, the reaction force should be the summation of the weight plus PV, which means that this is a large value, right? And that's it's another good situation for us to be in. But on the other hand, if you are pulling this way, you will resolve into this direction, into the vertical direction going up and to the right, and the reaction force now is the weight, but you will subtract from it PV because it's in the opposite direction of the weight, which means R is a small value. Now, if R is a small value, if you multiply it with the coefficient of friction, it's a smaller value, so it will be easier for us to actually pull rather than to push. So all of this explains the concept, and that's the basics of the basic thing that we would like to consider when we look into our daily activity, especially in biomechanics and in sports. And so it's very important to keep the friction in your mind when you're designing devices or wearables for sports or for biomechanical analysis. So that's very important to keep in mind. And one of the examples about this is mechanical behavior of bodies. So we have the coefficient of friction between the dancer shoes. So it's not just the direction of the forces, but it's also the coefficient of friction of the bodies, which is the shoes and the floor. They must be small enough to allow freedom of movement for the dancer, and the freedom of motion, but large enough to prevent slipping. And that's something that biomedical engineers actually deal with and design and work with, especially for wearables to specific applications or performances. Um, we also need to consider, because in statics and dynamics we learned about the solid objects. We studied solid objects, but now we can look at rolling friction between a rolling object and a flat surface. So we can need to consider the friction carefully, because we have the curved we have curved objects and we have flat surfaces, and sometimes the flat surfaces could be deformed during contact, so we don't have solid objects, and that is influenced by the weight, radius, and deformability of the rolling object. So the coefficient of friction of the two surfaces need to be identified. And one of the things that biomedical engineers do actually, a large amount of work in, is actually studying friction for wearables, specifically if they're doing biomechanics or biomechanical analysis. So in summary, if you would like to look at the big picture about what is the role of friction in daily activity and sport. So friction, is a force that opposes the relative motion of two objects in contact, and we need to keep that in mind when we design anything for human motion analysis or human performance or wearables. It is the force that allows us to walk without slipping, and we talked about the ballet dancer example, to hold also on a doorknob. So we need to make sure that we actually have the friction, coefficient of friction of the doorknob, allowing us to use it without slipping, and also to drive a car. Friction has also played an important role in many sports. For example, it is the force that keeps a baseball from slipping out of the pitcher hand, and that's something that we make a lot of testing to assess this friction coefficient of the baseball in the pitcher's hand. And also it's the force that allowed the golfer to hit a ball. So all of these examples are external examples, right, on the macro scale in biomechanics, but also we have examples inside the body. For example, if you are working in a company that designs total joint replacement for total hip or total knee replacement, we have moving parts and we have friction between the metals and the ceramics and the polymers that makes up the part of the total hip or the total joint. So we need to make sure that we as biomedical engineers able to assess friction coefficients, as well as to study the effect of the different what is the effect of the weight, as well as the other geometrical factors that can affect the friction force. Thank you for watching. If you reached this point, I hope this was helpful, and we are going to be doing a lot of examples in the class when we meet, friction examples, to make sure that we also understand the concept you know very well. Thank you for watching. Until the next video, bye.